We typically associate AI with screens and data centers, but in 2026, it has transitioned into the physical world, entering real-world industrial spaces. For decades, factory robotics followed a rigid pattern. Machines were bolted to the floor, lacked any visual perception, and were limited to repeating a single motion over and over in a safety cage. The 2026 shift introduces physical AI. This involves intelligence designed specifically to navigate and interact with the unpredictable variables of a physical environment, rather than just processing data on a server. Major industry players are now moving these units out of testing. Tesla, Figure AI, Boston Dynamics, and Digit are leading the effort to integrate these machines into existing supply chains. The technical divide between digital logic and physical execution is narrowing. These machines are moving from controlled research labs into active human workspaces. To understand this, we can look at a typical warehouse loading dock during a new deployment. This is where the hardware first meets the environment. The Boston Dynamics Atlas model is built with complex articulation. Its bipedal design is scaled to a human height, allowing it to move through spaces originally designed for people. In contrast, Agility Robotics Digit features a specialized head packed with sensors and a distinct leg structure. These joints are engineered specifically for the stability needed in high-volume warehouse logistics. However, these mechanical frames are static without a control mechanism. The hardware requires an autonomous system to make it functional. This is the AI agent. It acts as the robot's brain, constantly ingesting sensory data to build a digital map of its surroundings in real time. The agent uses this map to plan sequences, identifying precise grip points and calculating a spatial path before moving. The hardware provides the physical force, but the AI agent provides the coordination. It serves as the bridge, translating abstract digital logic into real-world movement. Once the system is online, these units move from the loading dock onto the active floor, beginning their shift alongside human employees. Currently, these machines can perform several measurable tasks: lifting objects, walking unassisted, and following instructions to use standard hand tools. This highlights the primary barrier to adoption. Human labor is a steady operational expense, but acquiring humanoid hardware requires massive upfront capital. A secondary graph tracks execution speed. Currently, robots operate slower than humans, though the technology is undergoing iterations to improve reliability. This creates a significant dilemma for early adopters. The capability is proven, but the high costs and current speed limitations make large-scale deployment a financial risk. As these machines become more common, the focus shifts to the human workers who now share the assembly line with them. For corporations, the long-term goal is a reduction in costs. Automating physical labor offers a path toward operational efficiency that isn't limited by human shifts or fatigue. However, these efficiency gains introduce societal risks. The displacement of manual labor could lead to significant economic shifts for the workforce currently responsible for these tasks. While this rollout is starting in the supply chain, the development roadmap suggests these AI assistants will eventually move into hospitals and private homes. The first deployments have begun. While the transition is currently expensive and slow, the arrival of these units suggests the future of manual labor will no longer be an exclusively human domain.